Ballet is a type of dancing which conveys physical beauty and typically a story to audience members. It began in the 15th century and has completely evolved since, with increasingly hard and physically demanding steps. In order to understand how dancers perform such incredible movements, we can learn about the physics of ballet's hardest steps. Attitude, derriere, balance. This is a static balance because it carries no net force or torque, and it occurs over the axis of rotation in the center of gravity, or the point at which an object will balance. In this case, the dancer's body is aligned over her supporting foot. The forces that act upon the ballerina are gravity, pulling downwards, and support from the floor, pushing upwards. These forces sum to zero, pointing through the center of gravity. The torque sums to zero because there is no rotation occurring. This allows the dancer to remain stationary while holding her pose. Also, the position is not completely vertical, as the lifted leg is at a 90-degree angle with her supporting leg, pulling the dancer backwards. To counterbalance this force, the dancer leans forward very slightly with her upper body, which can sustain the equilibrium necessary in balancing. This relates to Newton's third law of physics, which states that every force must have an equal and opposite reaction. Fouette turns. To start, the dancer pushes off with her foot to generate torque, a measure of how much a force acting on an object causes that object to rotate. When turning, the dancer must combat the forces of friction between her point shoes and the floor, as well as between her body and the air, which decreases momentum or the quantity of motion of a moving body measured as a product of its mass and velocity. To maintain rotation, the dancer flattens her supporting foot and then rises onto point, pushing against the floor and generating torque. Her arms and leg opens to her side at 90-degree angles to keep balance while slowing down because of the increased friction with the air, before generating new torque by bringing her extremities toward her body. When the leg bends in, the stored momentum of the leg is transferred to her body, which propels and rotates her as she rises onto her point shoes. As she extends and retracts her leg with each of the 32 turns, momentum continually travels back and forth between her leg and body, keeping the ballerina in motion. Sauterelle jumps. Ballerinas are seen leaping into the air while extending their front leg from a bent knee position into a split or oversplit with both legs fully straightened. When the knees are bent, the ballerina increases the amount of time that the upward force acts upon the body, which increases the height of the jump. In the air, the initial velocity will decrease as she reaches the maximum height when the velocity is zero. When returning from the air, the dancer will move in the opposite direction with a negative and increasing velocity, while accelerating until she returns to the ground from the gravity pull. This type of jump forms a parabola shape and can have a floating illusion, created by having greater force by pushing off the floor from a deeper plie. This will give the jump more momentum as well as height, which will allow the dancer to stay airborne for longer periods of time. In understanding the physics behind the steps, we can gain a better understanding about ballet, which was created to depict ethereal and magical ballerinas and can now be broken down into scientific concepts. Ballet isn't magic, it's physics.